Running a technical startup is hard. There are two main cost components that come when you run a startup. The first one is the payroll cost, and the second one is your infrastructure cost. Because the product you are selling is essentially software, that is your critical core business. In this video, I will break down how I have been running my startup for the last few years, the amount of cost we pay for the infrastructure side, how the infrastructure for Fermion looks like, and what you can take away from this video in order to build your own startup. Part of running a technical startup also involves making careful decision on how components work, how your data is stored, how the services are organized, and overall how scalable and reliable your system is. So in this video, in order to promote all of that and give you the breakdown of how much does it actually cost to run Fermion, I will be using Miro. Unlike any other whiteboard tool, Miro is an innovation workspace built for teams to collaborate together and work in a visual way. Now, I'm using it for building a software architecture and explaining you how Fermion works, but you can basically use it for pretty much any other use case, including brainstorming ideas, planning out product features, products themselves, and so much more. What also makes Miro unique in our case specifically is that it also provides integration with cloud providers like AWS, which we will be using in this video to figure out the final cost of running a platform like my startup. It has this library of components which I'm excited to share with you as we proceed with Fermion. And of course, AI-powered features to help you quickly create diagrams that explain concepts visually. I want to thank Miro for sponsoring this video, and now let's start with building your own startup. Alright, so let's take a look at what all technologies we use. So I'm going to go ahead and start adding diagrams from AWS directly. So if you go into diagramming shapes and search for AWS, you will find a lot of services over here which would cover our use case. Now, apart from an icon which makes sense, which looks like the service itself, this is also useful because we would be able to compute the costs directly. So I'm going to go ahead and create a basic version with AI so that we get a quick outline of things, and then we can replace the diagrams with the associated AWS technologies. So let's start with our backend. On our backend, we extensively use AWS Lambda, which is a technology to allow you to run code serverless, right? And we use AWS WAF to secure it. So I'm going to create a diagram here and let's see what it does. So you can see that it gives us a little diagram which does not include AWS services, but it's just a plain simple diagram and it gives us what we want. So this can also be used for prototyping and just creating various things, right? So right now I have told AI exactly what I need to do, but you can also just randomly ask it how a backend structure would look like. So let me first make you understand how the technology exactly works, right? So in the diagram itself, the user would just connect to an AWS Lambda instance directly, right? And with AWS Lambdas, you know that there is a concept of function URLs now, which makes it possible to not have AWS API gateway in front of it, right? But you can still have AWS WAF on top of that. In fact, there should be an AWS CloudFront here because in order to give a custom domain to a AWS Lambda URL, you need AWS CloudFront distribution, right? So in reality, it's AWS WAF, then AWS CloudFront, I'll add that, and then AWS Lambda. Now our backend code is all of that is written in Node.js, which runs on AWS Lambda Node.js. It now interacts with various services like SES for sending emails, right? So if you're using anything expensive for sending emails, you should probably consider AWS SES. It's a great service and it's very, very cheap. Then it writes all its logs to CloudWatch so you can see and query the logs if you have any errors or if you want to debug something. And then obviously it also connects to RDS database as well. This is a V1 diagram. Let's just try to make this much more detailed now. So what I'm going to do next, I'm going to start replacing these services with the actual services which we use. So I'm going to delete this RDS over here, and in the diagramming shapes, let me just search for RDS directly and let me add it over here, right? So this is what our Lambda interacts with. Similarly for SES, I'm going to use Amazon's simple email service, which is AWS SES, and then finally CloudWatch as well for the logging part. And of course, to make this whole complete, we also need AWS Lambda in the picture. Now, as I mentioned, AWS CloudFront actually sits on top of AWS Lambda. So the rerouting of the subdomain is done by CloudFront. And then finally, we have the WAF, which is what we use to block IP addresses and malicious users. And I just added a couple of more entries over here, which is like a desktop and a user trying to access your services. So this is how they will start to access it, right? They'll probably write backend.codedump.com/API/whatever, not them directly, but their browsers would write that. The first endpoint which they would hit is an AWS web application firewall. Then they would move on to CloudFront. Then inside Lambda, they will have access to everything. Now, one more thing which you have to realize is that this whole thing over here, this is inside a VPC, right? So this is a VPC, which is a virtual private cloud. Now, I'm not creating a component for VPC because VPC by nature is free of cost. You are just only paying for the services inside that. But the reason this is in VPC is because the RDS instance, the Aurora instance, which you see over here, this is not available on internet, right? So this can only be accessed inside this whole thing. In fact, CloudFront is also not in VPC as per se. AWS Lambda is the one which is in VPC. Now, this is one of the many components of running Fermion as a company. Let me show you all the feature sets we have which are critical in this pipeline. So first things first, when you visit any website hosted by Fermion, which is our platform, when you refresh this, you're going to see that there's a split second of time when it loads the data from backend. So this call, what happened just now over here, this is going through this whole infrastructure, right? When it was deployed on AWS. But there are many more things which also happen. For example, crunching some of this data like enrollment trends or revenue, or even if you look at things like analytics, there are a lot of data points, especially if you go back to past, which can be done over a cron, right? Where the data doesn't change much. So we also have an infrastructure of running a lot of cron jobs within our VPC, right? And these cron jobs are actually running on Lambdas themselves. So you know that AWS Lambda can be connected to an event bridge, which then can be triggered, which then can trigger a cron based on like whatever expression you provide, right? So this over here, which you see, is also part of VPC. The reason being that it still has to access the database. This instance, this whole group would also have to call database. And by the way, we have like a lot of Lambda. So it's basically like one Lambda per cron, which is a pretty standard practice. Now, the second thing you have to keep in mind is that one of our biggest components of cost is also the content delivery. So just to give you an example, if I show you the internals of a school that runs on Fermion, for example, the SQL bootcamp, if I continue learning on the SQL bootcamp, you will see the instructor over here takes live sessions, which are like, pretty much 4 hours, more than 4 hours in duration, and the users can access this live session anytime they want. Now, this live stream has to be stored somewhere, right? This video has to be stored somewhere. And for that, we choose S3. So let me show you how this streaming infrastructure works. So there are two parts to this streaming infrastructure. The first one is the ability to stream the video once it has been processed. And the second one is processing the video itself. So let's talk it one by one. Let me just label this real quick. So this is like our general backend. This is going to be video delivery. And the way this also works is pretty similar. You have an AWS Lambda instance, which in general is our backend only, which can talk to an AWS S3 bucket, right? And the reason what it has to talk about is the pre-signed URLs, because you see that you don't want to keep your bucket fully open. You don't want these contents to be open. That is why you need a compute layer in between that creates like sort of pre-signed URLs over here. So these URLs, when you create these pre-signed URLs, what it would mean is that you are just giving access for this specific video for some time to this user. So maybe let's say at some point their enrollment is complete, or they just refund for the course, or whatever happens, then that URL is no longer valid. And the way this video streaming in general works is a technology which we call as HLS streaming, right? So this S3 bucket over here, this contains HLS streaming video files, which are like many .ts files and one M3 UID, which is a manifest file. Now, I have discussed in detail how HLS streaming in general works on my previous videos, so I will not get into details of that, but you can learn about that from my past videos. But this is like one way to stream videos on internet, right? Now, this is video delivery, which is pretty simple. I mean, nothing complex over here once you have stored the videos on your stack. What is, however, a slightly complex process is the video transcoding. Now, you can go ahead and use like Media Kit. You will see like there are, in the diagrams, you can see there are media elastic transcoder and services like this. You can go ahead and use that, but we don't do that because the cost is just too much. The cost can be minimized if you use AWS EC2 instead of your typical Media Kit, right? Now, the way this architecture works over here, the way we have made it work is again that we have an AWS Lambda, a Lambda instance, which is sort of a cron, right? So it's sort of a cron that runs every minute or so, and it checks if there is any new message in the queue for any new video to be processed. And if there are new messages, what it's going to do is it's going to launch a bunch of these EC2 instances, right? As many as it takes. This could be completely arbitrary depending on like how many instances, we need at that point. So for example, if I frame this, you can see that this can just launch any number of arbitrary instances. And this can also just pin them down once the work is done. Now you would ask, hey Mehul, how would this SQS know that, there are some videos to be processed? Again, S3 comes to our rescue. Because with S3, what we can do is that from a client's point of view, S3 can just directly accept uploads, right? So what we will do from a client point of view is that we will ask the instructor to upload the video directly, right? So they will upload the video directly to the S3 bucket. This S3 bucket in turn is connected, this over here is connected with SQS, right? So anytime an S3 bucket gets a file, it automatically gets registered into SQS through a CloudWatch alarm. Once SQS gets some data, it can invoke Lambda, or your Lambda cron can just poll SQS, and it can finally then handle a pool of EC2 instances to transcode all the videos which are uploaded in this temporary S3 bucket, and then finally upload it to the bucket once all of that is done, right? So these EC2 instances can upload the transcoded videos to S3, which by the way, this is the same bucket as this, right? So maybe I can just probably link them directly over here. So this also concludes another important part of running Fermyon as a platform where the video transcoding takes place. The final thing in our stack, which is slightly complex, is the ability to run coding labs. So if I go ahead and show you another course on Fermyon, and if I show you this very basic coding lab, for example, in Solidity, you will see that right now there is a real virtual machine which is getting provisioned, and within a few seconds of time, you will get a full-blown IDE environment right inside your browser. Now, this environment can run anything, right? Whether that's a Java Spring Boot project, whether that's Python, whether that's Django, Node.js, Express, anything. And it's a real server, right? So it cannot be a Lambda or things like that. So how does that work? So again, the way this works is that the user pings our backend Lambda, which again maintains a queue of requests, right? Where because if let's say we have many users coming for playgrounds, we just don't want the system to crash. So it maintains a queue of requests on which user needs to get what playground, and the backend which we have just registers that request. Then there's another compute instance which sort of acts like an instance that is supposed to register all these requests and give them containers, right? So consider this as a sort of a master instance that reads this queue. And once it reads that, depending on the capacity, it would either upscale the system, this system if required, so it can create more EC2 instances. And on these individual instances, it will start different containers, right? So one of these containers get automatically assigned to the user that is requesting them once this whole process happens, right? But the basic idea is that you create a request inside Lambda, through Lambda inside a queue, and then you have a master node that is supposed to control the whole pool of instances and give a container from it to the user. This is how this container works, right? So the container which you're seeing over here, the place where I am, this is one of the containers inside one of these EC2 instances. And it could be like arbitrary, random. And again, the work I am doing over here, like making any modifications or anything, that is yet again stored in an S3 bucket. So every container over here is smart enough to synchronize with the S3 bucket directly, and depending on the user also, it's able to synchronize that what user has what work stored, right? So all of your work, whatever changes you are making, are directly synchronized with an S3 bucket. This is how the architecture looks and works like. Now let's try to figure out the cost for running something like this. And this is where this gets handy, because now we can associate all these costs with the cost explorer tool we have. So if I go ahead and select all the elements over here, and if I click on this plus and AWS cost explorer, cost calculator, you can see we have a bunch of these options where we have to now start setting up costs, right? So let's start doing that. Let's start with a simple few things. So let's start with simple email service first of all. So with SES, we roughly send close to, I think, 100,000 emails a month right now. And of course, like once we give more tools like marketing tools and so on, this count would obviously increase. So I'm just gonna switch this to per month. We don't usually send any attachments, so that's completely fine. We can just keep it 0. And we don't also like more or less receive emails through SES, so that's fine. We don't have any dedicated IP addresses, so that's also fine. And we don't have virtual delivery manager enabled because it's just like some extra cost, right? So you can see We already started getting a few numbers. Now, just with SES itself, it's showing us that it costs us $25 a month to run, which is great, right? Because now we can just start getting a little bit of idea about every single service. So now let's take a look at this Lambda. And if you take a look at this Lambda, this is our core backend, right? Now this is like serious stuff. So we use x86 architecture. The number of requests we get is close to 50 million right now. Duration of each request is close to 100 milliseconds, and the memory is 1 gigabyte. Ephemeral storage, I think 512 is included, so that should be good enough. And let's try to calculate this again. And you would see that now we have a little bit of more bill now to worry about. So let's keep going. Next up, we have CloudFront, which again corresponds to some of the huge data transfer we do, one of the most data transfer we do on internet. So this includes a lot of countries breakdown. I would probably just stick to United States and just give you a rough estimate. So in terms of terabyte of data transfer per month, I think we do close to like 5 terabytes right now. We don't do much of data transfer to origin, so we can probably keep that as 0. And in terms of million requests per month, here also we can say that we do close to like 5 million requests. Let's save that. Let's move on to WAF now. We have one access control list, which is there. I think it's rather 2. I don't exactly remember, but it was either 1 or 2, but it doesn't matter. Like the cost is like small per list. So this is per month. And if we look at million per month, it would be again pretty much similar to how many requests we get for our Lambda instance. So WAF is not a huge bill, but it still is relatively big. Then this Lambda over here, which we have, these are like cron instances, right? So we'll just probably keep crons over here. And crons are pretty much very, very cheap. So let's say even if we are running request every minute, right? Which is like a cron every minute. Number of minutes in a month is about 438,000. No, not even that, 43,800. So it's probably like, this is for one Lambda, one cron. I think even if we have like about 10 crons, so it would be like close to 500,000. Duration of each request over here, it could be slightly larger because crons are supposed to do like big tasks. So I would probably say up to like 20 seconds. Amount of memory we usually keep 102 for 1 gigabyte only, and 512, which is the default. And I think this is like slightly aggressive. We can probably drop the number of requests because I just checked, we don't get this much data. In fact, let's just drop this to about 512 because our crons don't need that much RAM. And plus even the request for each cron, I think pretty much is not 20 seconds. It's probably about 5 seconds or less, I would say, because most of the crons just end up doing nothing. There is no work to be done, especially in the ones that are running continuously, right? I think 5 seconds is a good amount as an estimate. Now, all right, let's keep going. This Lambda over here, I would not add the billing for this because again, this is part of our backend itself. Yep. This storage is, again, I'll just keep S3 in general, the general purpose storage. The storage we have runs close to like about 3 terabytes right now in size. So close to like 3000 gigabytes. EC2 instances also, let's just define over here itself. So you see this is the video transcoding infrastructure, right? So on average, we are probably running maybe like 2 instances all time, and we use C instances because transcoding is like CPU intensive. So probably like C3x large is a good estimate, and utilization per percent per month is 100%. So that's completely fine. We can just assume 2 instances randomly like running throughout the month, even though this is not the case. This upscales and downscales according to the usage. We can even have 10 instances, but at a 50% utilization and so on. So that's not a concern. Let's just keep this 2% and 100%, and we are doing on demand right now. We actually do spot, by the way. Sorry, I forgot. We do spot instances. I just saw this option and I then figured out. So spot is something which is like a perfect use case for this transcoding, because even if this instance gets killed, we can just always retry the transcoding, right? Then we have another AWS Lambda, which I'll again probably not use because this is also sort of like a cron only, which we already covered above. And then for all these AWS instances, which are the playground instances, let me just pick one. So this would again be, we use some sort of M6 instances over here. Let's see if we have those. Yep. So we have M6A large, which is exactly the instance size I think we use. And on average, we have like 5 to 7 instances pretty much running in the night time. And in general, like, if I average it out across days and nights, it would be like close to 5 to 6 instances. That means I think it's M6A X large because we run 10 containers per instance. So that means like 60 users on average anytime. In daytime, it probably shoots to about 150, 200 at peak hours. But other than that, in the night or when the usage is low, it just shoots down to like 30 or 40 users also. So we have M6A large. We have on demand for this. There is no spot instance over here because you can't just terminate user sessions. So there we go. And last but not the least, let's just figure out the RDS. So we do use Aurora Postgres, and I'll have to check exactly what our instance size was. We were mostly able to get things done with 2 vCPU and 16 GB RAM, but occasionally, like under heavy load, I do remember one time when we had like 4 vCPU and 32 GB RAM also going on for a few days. So, but for the most case, I'll think DB R7G large is a good estimate for us. So a bill of roughly 1600 USD and combined with RDS cost, which is usually around 900 to 1000 USD a month, that's close to about 2600 USD a month. Now you might feel this is too much, and that might be true. And that is why there are a lot of solutions for these which are not as reliable as AWS, but they can still get your job done at a much lower cost. For example, changing Lambdas to EC2 instance and using better alternatives than using CloudFront for your data transfer, right? So there are cheaper CDNs you can use. Yeah, I hope this overall gives you an idea of how costly it is to run a startup. And I hope this video was also useful for you to understand how different things can be split down into various components. And that's all for this video. Hopefully this helped you understand everything it takes to run a startup from a technical point of view specifically. And if you're starting your own venture, I wish you all the best. And again, thanks to Miro, which is an extremely important tool for visualizing and learning about technical concepts like cloud computing. I hope its integration with AWS in this video helped you understand the cost extremely clearly and probably much better than how AWS itself shows it. Whether you're brand new to cloud computing or an experienced developer, I recommend checking out Miro not only for these technical diagrams but also for your own personal use case, because Miro and Miro AI can help you save a lot of time while developing a deep understanding of technical concepts like these. Do check out Miro, the link is in the description, and let me know in the comments if you have any questions. That is all for this video. I hope to see you in the next one very soon.